Welcome to this concept explainer, brought to you by CBSE ScoreLab of ProfSam.com. That is ProfSam.com. Today, we are starting a deep dive into a very important concept from Unit 2, Electrostatic Potential and Capacitance. The topic is potential energy in an external field, and we promise a very, very simple and exam-safe explanation that you will remember for life.
That sounds really good because potential energy can feel a bit abstract. I mean, when we have two charges, Q1 and Q2, creating their own field, it's straightforward. But when some other field is already present, I always get confused about which energy belongs to whom.
Absolutely, and that is the exact confusion we are going to clear up today. So let's start with a simple question, something from, right inside your kitchen. If we place a single water molecule, and, water molecule is a tiny electric dipole, right? It has a permanent dipole moment.
Yes, a positive and a negative end.
Exactly. So
Yeah.
if we put this tiny molecule inside a microwave oven, inside its strong electric field, how does that molecule know which way it should turn?
Oh, that's a very specific example. I thought energy was just about attraction or repulsion.
It is, but here's something surprising. You can take that water molecule, that dipole, and place it in a strong, uniform electric field. And it will feel, it will feel zero net force.
Wait, zero net force. But if the force is zero, then it shouldn't move, right? So where does the energy even come from? It shouldn't have potential energy if it's not moving.
That's the perfect question. It won't accelerate linearly. It will not move from one end of the oven to the other, and yet it possesses potential energy. The energy is stored as the ability to rotate.
So it wants to twist.
It wants to twist. So why does it have this potential energy if all the forces are perfectly balanced? That is our deep dive mission for today. Generally, we calculate the energy of a charge system where, the charges themselves are creating the field. But here, we are calculating the energy of charges that we've dumped into a field that already exists, an external field. So the total energy actually comes from two very distinct sources.
Two sources. So we have to track the energy from the external world and the energy that charges create among themselves.
Precisely. Let's use an analogy to make this crystal clear. Think of it like this. We are climbing a ladder with a backpack.
Okay.
The ladder and the Earth's gravity, which is already there, right? That is the external field. The work you do against gravity to climb that ladder, that's the interaction with the external field.
So that's like the work done against the external potential, V, the QV term.
Perfect. Now think about the backpack itself. The weight of that backpack, the strain on your shoulders, that is the energy of the internal interaction.
You mean between the charges in my own system?
Yes. So the total stored potential energy is the sum of both these things. It's the work to climb the ladder plus the internal strain of carrying the backpack.
That makes a lot of sense. So the energy depends on the height of the ladder, which is the external potential, and how heavy my backpack is, which is the internal system.
Correct. And this idea is so important because in real engineering, like in particle accelerators, we often place charges into a very powerful, pre-existing external field. Imagine a flowing river. That's the external field. Now you drop two boats, your charges, into it. They drift with the river, so that's external energy, but they also, bump into each other. That adds internal energy.
That visual really helps, the river and the boats bumping into each other.
Now let's see how NSERT defines this, and we'll start with the single charge case first.
Okay.
Could you read the definition for us?
Yes. It says, potential energy of charge Q at a point in the presence of field due to any charge configuration is the work done by the external force, equal as opposite to the electric force, in bringing the charge Q from infinity to that point.
Thank you. Now let's unpack that with a formula. The definition for a single charge is very direct. It's just U equals Q times V of R. So potential energy is simply the charge multiplied by the external potential at that point.
So for a single charge, it's only the climbing the ladder part, because there's no one else to interact with.
Yeah, exactly. No backpack, no internal strain, simple. Now let's move to a system of two charges, Q1 and Q2. This is where the backpack comes in. The total potential energy U now has three parts. First, the work to bring Q1 in. That's Q1 times V at position R1.
Okay, that's the first person climbing the ladder.
Right. Second, the work for Q2. That will be Q2 times V at position R2.
Makes sense.
And the crucial third term, the one everyone forgets, is the energy of their mutual interaction. Because when you brought Q2 in, Q1 was already there creating its own field.
The backpack weight.
Backpack weight. That's Ko times Q1, Q2 divided by R12.
So the total energy is the sum of all three.
Yes. U equals Q1 VR1 plus Q2 VR2 plus KQ1 Q2 over R12. Hope everything is clear so far. This concept explainer is from ProfSam.com. That is ProfSam.com. All right, so the second major part of this topic is the energy of a dipole in a uniform external field, E. The potential energy in this case is U equals minus P dot dot E.
The dot product.
Yes, which is minus PE cos theta. Let's do a simple worked example in our heads. If our dipole is fully aligned with the field, what is theta?
0. Theta is 0.
Right, so cos of 0 is 1. The energy is U equals minus PE cos of 0, which is just minus PE.
And that's the minimum energy state, right? The most stable position.
Exactly, that's its most relaxed state.
Yeah.
Now, to twist it 90 degrees, we must do work. The work done would be the final energy minus the initial. At 90 degrees, cos is 0, so U is 0. So the work is 0 minus PE, which is plus PE.
So the work you do gets stored as that potential energy.
Perfectly put. And this whole discussion on dipoles and their alignment, this is actually the foundation for our next big topic,
Which is?
understanding polarization of dielectrics in capacitors. So what we're learning now is essential for that. Okay, now let's move on to the exams. There are two major misconceptions that cost students marks. Let's kill these silent killers right now.
Okay, ready.
Killer number 1. Students often write that potential energy belongs to a single charge, especially when they see U equals QV.
Right, because the formula looks like it's just for Q.
But that's a wrong idea. They forget that V itself is due to some external source. The correct idea is that potential energy always belongs to the system of charges, to the interaction. I always tell my students, it takes two to tango. You need two things for energy to be stored.
So if I see U equals QV, the U belongs to the system of Q and the external source, never just Q.
Perfect. Now for killer number 2, this one is about the dipole. When asked about the dipole, students often think the potential energy is 0 when the dipole is perpendicular to the field.
Oh, at theta equals 90 degrees.
Yes, and they get confused because the torque is maximum at 90 degrees.
Ah, so they mix up torque and energy.
They do,
Yeah.
but the correct answer is that U is 0 at 90 degrees simply because that's the reference point we chose. The stable state, the aligned state at theta equals 0, is actually the minimum energy, which is minus PE, remember. Aligned equals happy equals negative energy, relaxed.
So aligned is the true minimum, the most stable state.
Exactly. Now for our memory anchors. To keep this energy concept straight, always remember the phrase, aligned is fine.
Aligned is fine. I like that.
It tells you that when the dipole moment is aligned with the external field, the system is fine, it's relaxed, and it's at its minimum potential energy. For a physical anchor, imagine you're holding a compass needle.
Okay.
When you let it go, it aligns with the Earth's magnetic field, right? That's the external field. That relaxed, aligned position is the negative potential energy state. Any work you do to twist it is stored as potential energy.
So the compass needle trying to snap back is the energy being released.
That's it. You've got it. All right, let us summarize the most factual, exam-safe points about potential energy in an external field. Point 1. The total potential energy of a charge system in an external field is the sum of the external interaction energy, which is all the QV terms, and the internal interaction energy, which is the sum of all the K key QJ over right pairs.
So external plus internal.
Yeah.
Ladder plus backpack.
Point 2. The potential energy of a single charge Q is simply U equals QVR, provided VR is the potential due only to the external sources. And remember, it belongs to the system.
Right. The system of the charge and the source.
And point 3. A dipole moment P placed in a uniform external field E has potential energy, U equals minus P dot BE. And this is minimized when the dipole aligns parallel to the field when theta is 0. To score maximum marks in 12th CBSE Physics, Chemistry, and Math, visit ProfSam.com.
That is P-R-O-F, Sam. Right?
Yes, ProfSam.com. And just one final thought for you to think about. What if we put a conductor into an external field?
A conductor. The potential has to be constant everywhere inside and on it.
Exactly. So if the potential V is the same everywhere, what does that imply about the potential energy, U equals QV, for any charge inside that conductor?
It means U would be the same at every point. So the work done to move it from one point to another inside the conductor would be 0.
Which perfectly reflects the fact that the electric field inside is 0. The energy state is constant, even when the external field is strong. Study hard, and all the best.